If you are looking for an easy to use regenerative energy source nowadays, then your best bet is to utilize solar panels. By simply shining light on them, they can create an output voltage that is capable of powering small loads or even bigger ones if we increase the size of the solar panel. But how can we reach their maximum power output? And how do we have to wire them up to, for example, charge up a battery? Let's find out. If we have a closer look at this 100 watts solar panel, we can see that it consists of individual solar cells. Those basically make up all commercially available solar panels. And of course, you can buy such cells online as well. After soldering a tap wire to the front as the minus terminal and the back as the plus terminal, we can use a multimeter to measure a voltage of around 0.5 volts when light hits the cell's surface. That is pretty much the maximum output voltage of one cell, which is also the reason why a solar panel connects many of those cells in series in order to increase the output voltage. My 100 watt panel, for example, connects 36 cells in series to create an open circuit voltage of around 14.3 volts. But if you are now thinking about soldering many bare solar cells in series instead of buying a proper solar panel to save a bit of money, then it is noteworthy that those cells are extremely brittle and thus can be hard to work with. So having a proper housing for the cells is definitely worth the money. Now, if we have a closer look at the smaller solar panel, we can see that it consists of 12 cells in series. But creating such a series connection also has one big negative side effect. Just imagine that a cloud could partly prevent light to hit the complete surface of the solar cell. That means that one part of the series connection now features a much higher resistance. And since current needs to flow through all the cells, the power output would decrease drastically. As an example, we can hook up a 5mm red LED which draws 3.8 mA from the solar panel and thus creates an output voltage of 1.76 volts, which equals an output power of 6.7 milliwatts. But if I cover the last two cells of the panel, so 1/6 of the complete surface, the LED only draws 2.2 mA at an output voltage of 1.71 volts. Which equals an output power of 3.8 milliwatts. That means the power decreased by 43% while the surface area only decreased by 17%. That is terrible. To solve this problem, we could add so-called bypass diodes in parallel to each cell, so that current could flow through it instead of the high resistant solar cell. Obviously, with panels this small, this does not make much sense. But if we take a look inside the junction box of the 100 watt panel, we can actually see two diodes. Those are placed in between the half of the solar cells and the plus and minus terminal. Of course, this is not the ideal solution, but through the two diodes, the panel can uphold the power outputs if one half of the panel is darkened by a cloud or something similar. Another kind of diode you often see are so-called blocking diodes, and are used when solar panels are connected in parallel, in order to decouple them from one another and prevent reverse current flow through them. And now that we know how solar panels are wired up, it is time to use different loads to test out their power output potential. But to lower your optimism right from the start, we will probably never get 100 watts from a 100 watt panel, since those characteristics were determined under so-called STCs. aka standard test conditions. Those include an irradiance of 1000 watt per square meter, a solar cell temperature of 25 degrees Celsius, and an AM value of 1.5, which means that the sunlight traveled through an air mass of 1.5 times the value of the atmosphere. With my 0.6 watt panel here, for example, I achieved an output power of 16.5 milliwatts with a green LED, an output power of 13.2 milliwatts with a blue LED, and an output power of 9.5 milliwatts with a red LED. But why does the output voltage vary that much depending on what kind of load I attach? We can find the reason by having a look at the simplified equivalent circuit diagram of a solar cell. If no load is attached, so an open circuit, it acts like a constant current source that lets a current flow through a diode, which therefore creates the characteristic cell voltage of around half a volt. Parallel to that, we got a resistor, which represents the power losses caused by the semiconductor material defects. And at the end, we got a series resistor, which represents the power losses through wires, terminal connections, and so on. If we now add a load to the cell, the current from the constant current source divides itself and creates a more complicated electrical network. But what we know for certain is that by varying the load on the outputs, we should be able to find an optimum at which we can draw the most power from the cell. So I got myself my DIY power logger, hooked up the solar panel with a 5 kilo potentiometer load, inserted a micro SD card, and started slowly decreasing the resistance of the loads, while simultaneously the constantly changing voltage and current values were saved on the SD card. Afterwards, I imported the acquired data into Excel and created a suitable XY diagram. After printing it out and connecting the dots to one another, we can see two characteristic points. First off, the open circuit voltage, where no current flows, and the short circuit current, where there's almost no voltage. Those values are pretty much always mentioned on a solar panel. But what is also mentioned on my solar panel is the MPP voltage and current. MPP stands for maximum power point, which is not visible in my diagram so far. So I multiplied the current and voltage values and added a power line in the diagram, which makes our maximum power point easy to find. This point equals an output voltage of around 4.4 volts and a current of 4 milliamps. So a load resistance of 1100 ohms. Now of course you don't want to simply add a resistor with the required value to the outputs and be happy about that you can heat it up the most efficient way. You usually want to charge up a battery. That is where we can use charge controllers. The best ones of this kind are so-called MPPT ones, or maximum power point tracking ones. Those usually utilize some kind of switching converter to act as the ideal MPP loads and thus charge up the battery. Other, more inefficient kinds simply use PWM to charge up the battery, but they do not try to find the MPP and thus can decrease the efficiency of up to 30%. And with that being said, you already know quite a bit about solar panels and how to use them properly. If you learned something new, don't forget to like, share and subscribe. Stay creative, and I will see you next time.